This is Lab 1 charged tapes. The purpose of this lab is to calculate the amount of excess charge that an ordinary object like tape can have under normal conditions. We will observe the interaction between two pieces of charged tape and determine how much excess charge is on one piece of charged tape. These are the results of the experiment. The two tapes repel each other, the magnitude of the gravitational force and the magnitude of the electric force are equal, and the charge on the tape is shown here, and the number of electrons on the tape and number of atoms on the tape are shown here as well, and the ratio of electrons to atom is shown. These are the fundamental principles that we will be using. We'll be using Newton's second law along with gravitational force, which is force equals mass times acceleration. The acceleration is the acceleration due to gravity, which is 9.8 meters per second squared. We will also be using Coulomb's law, which is the force between 2 point charges, which is K is Coulomb's constant, the two Q's are point charge, and R squared is the distance between the two charges. It also tells us that positive and negative charges attract and then like charges repel. We'll also be using the electric field of a point charge, which is Coulomb's constant times Q over R squared R hat, and the electric force of a point charge is force equals Q times the electric field. The models of this system are, the system is tape B, the floating one right here. Surroundings are tape A and everything else. The procedure is to charge the two tapes by ripping them from another piece of tape that is laid down on a flat surface, and then observe their interactions by floating one on top of the other like seen here, and we'll use a code model to determine the excess charge on tape B. Our assumptions are that each tape has the same net charge evenly distributed across the entire piece. Each tape is treated like a point charge in the center, and air resistance is negligible. There are observations where the tapes repelled each other, which shows that they are like charges, and they are both positively charged as they were both attracted to the negatively charged pen. This is our free body diagram of the floating piece of tape. So tape B, we have force of gravity and force of the other tape, electrical field, and then these are the two tapes shown as point charges. These are our initial conditions and data calculations that we used in our code. So our tape length was this many meters, tape width was this many meters, our tape mass was in kilograms, and our distance when the tape began to float was in meters, and the area of an atom is this right here with meters squared. And all of these calculations were done in the code, which we show here. So we have our constants that I mentioned before. We have our objects. Those are our tape. This is tape B, this is tape A. We have our source and our observation location, which our source is tape A, this is tape B. And then we calculated our force of gravity and force of the tape, on tape's electric field on the other. And we then calculated the charge on the tape, the number of electrons, and number of atoms, and the ratio. So to get the charge on the tape, we had to work with the electric field and Coulomb's law in order to work backwards to get that Q equals the square root of force times R squared over Coulomb's constant, which is seen right here, and we get that the charge on the tape is this number right here, and the number of electrons, we take the charge divided by little q, which is the charge of one electron, and that will give us the amount of electrons, and then the number of atoms on the tape is the length times width divided by the surface area of an atom. And then the ratio is just electrons divided by the atoms. And then what was the magnitude of the charge on one piece of tape as calculated by your computational model? It is this many coulombs, as you can see. The potential error for this is that the charge may not have been equally distributed. Some of the charges may have been lost due to mishandling, and there could have been any inaccurate measuring of the tape. So what if electrons had positive charge and protons had negative charge? What would change about the observations you made with your tapes and other charged objects? So the two tapes would still repel each other. They would just both be negatively charged, and like charges repel, so they would still repel. And then the tape would also would still attract to the pen and other objects, as the pen and other objects would be oppositely charged still. So the pen would be positively charged and the tape would be negatively charged, which those attract. And then why is it important to handle the charged tapes as little as possible? What happens when the charged tapes comes into contact with your hands or other objects? it's important because our fingers and our hands will even out the charge if we handle it too much. So the tape would create a dipole with our hands and other objects, and the tape would then be attracted to said objects. The objects would kiss, and then the electrons would transfer over to the tape and neutralize it. Thank you.